Firstly, hello everybody, and thank you. Welcome to episode 4 of Talks by AI chapter at Sedin Technology. Today's talk is in participation with AI practitioners Chennai. With that being said, let me introduce you to today's host, who's Harman Sohanpal. He's a principal solution architect at Tarka Lab, which is a division at Sedin Technology, where he has led impactful project with cutting edge technology. With over 12 plus years of experience in platform development, program management, and technology leadership, Harman has worked on high profile projects such as IPL Trophy, Big Billion Days, and YouTube Brandcast. In today's session, he'll guide us to the worlds of LLMs, exploring how this model are reshaping industries, tasks, and approach to AI. With that being said, I'll hand the session to you, Harman. Just a quick note, everybody, whatever questions we have, we'll take it by the end of the session. If there's anything, please drop it in the chat box. Thank you. Over to you, Harman.
Thanks a lot, Sadhna. Hello, everyone. Thanks for joining the session, and really thankful to the AI practitioners Chennai for sponsoring this. So without further ado, I'll get started. I'll share my screen. Let me know if you guys can see my screen. Is it visible?
Yeah.
All right. So today I'll be talking about unveiling the power of LLMs, and I'm sure that everyone here would have heard about LLMs and this whole AI wave which has come up. And before we really dive into this, I'll touch upon briefly the last session that we did, session 3, where we talked about a RAG-based systems. RAG is pretty much like a retrieval augmented generation, and there we saw how we convert external data into vectors and then use the power of LLMs. Sorry. Okay. So the RAG is where we convert the external data that we have into vectors and then use the power of LLMs to get back the responses that we really need, right? But at that point of time, we never looked at what a LLM was, or what really a fine tuning of a LLM really means. So in this session, I'll try to touch upon what really is LLM, right? Why suddenly so much hype about LLMs? Why AI become a buzzword, and all those things. So a little bit about myself. As Sadhna mentioned, I have around 11, 12 years of experience in managing, developing, and scaling innovative products across various industries. Currently, I'm leading a team in an analytics aggregation company where I'm driving data-driven insights and strategies. And I've also delivered like big data and royalties analytic solutions for a leading music distribution company. I'm the founding member for the RAG-based Vidura bot that we showcased in the last seminar. And I've also experienced working with things like PostNet and Google Assistants, learning generative AI. But this whole PostNet Google Assistants was before the whole AI wave really came in, right? This is where the neural networks and deep learning is not something which has come up new, but it become accessible to the common world. And we'll look at like why this has happened and why the whole AI has become like so big in today's world. So before we start, I'd like to do a small exercise. I don't know if we can make this session interactive, but let's just see how we think as humans. Let's forget about AI for the time being. Let's forget about any software or any computer for the time being. If we see something and if I ask you a question, how would your brain really react? And if you guys can maybe just put down in your answers in the chat window, that would also be great. So the first one is this. So if anyone can answer this, I think that would be awesome. And we'll look at like why I'm getting into this piece here. And look at the second piece now. I say dash is a great way to start your morning, right? Now, there's a small difference between what happened in the first line versus what happened now. And let's say for breakfast, I always enjoy having this thing. And every Sunday, I sit by a window and sip my hot cup of dash, right? So what just happened, right? What is the relationship of this with LLMs or AI or whatever we are about to talk here? Now, if you look at the first question which I asked, right, I just had a blank statement. There was no context provided in there. Now, even as a human, we have learned so much throughout our journey, right? Whether it's a personal journey or a professional journey, we learn a lot, and then whenever we see a question, we try to use whatever knowledge we have from the previous learnings that we have had, and then apply that knowledge over to try to answer a question. But in the first statement, there was no context provided. It was just a blank statement, and it could be anything in the whole universe, right? For the second one, there was some context provided, but that context was that when I say dash is a great way to start your morning, the way our brain processes this is that we know what great means. We know what a start means or what morning means. And then we can say, then people can have different perspectives on whether Netflix is a great way to start your morning or walk, meditation, and this thing, right? For the next one, we knew what breakfast really means, right? And then enjoy is a word that we understand today. If I put something which we do not understand, which is like a completely different domain out of from what we work in, we might not be able to answer this question as well, right? And same goes with the next one as well, right? Every Sunday I sit by my window and sip my hot cup of coffee or tea, right? Now, hey, I see here's some noise. Thanks. So the reason why we are talking about these things is that I just wanted to put a correlation between how human brain works versus how LLM works. Because at the end of the day, what LLM is trying to do is it's the next word predictor actually. So it takes in a text and tries to predict what comes in next, which sounds very easy, and then we'll really see what really goes underneath that to come up with that next word, and why is that really changing the way we are looking at AI today. And all of this was happening, all of this neural networks, deep learning, and everything was going on, and then not much was importance was given to AI during that time, right? There were tech practitioners who were really looking at AI, but all of a sudden, this guy came into our lives, and then all of a sudden everyone became like an AI expert, right? Everyone wants to work with AI, they want to add AI to their businesses, they want to use AI for everything, right? Because it was not that AI, changed overnight, but AI kind of became accessible to a common person, right? Even a non-tech person started using AI for their day-to-day tasks and things, which would not have been possible before that, because training a model or things really took a lot of efforts and things. But now with all these pre-trained models that we have, it became really easy to use AI. So let's look at this. When ChatGPT came in, we got to know about this whole ChatGPT and everything during GPT-3, where it kind of became famous. But GPT came back in 2018. This was like the first generation. It only had 117 million parameters, and that introduced the transform architecture for large-scale language modeling. So we'll look at really what transformer architecture was and why this kind of brought in a boom for the AI piece. Now, GPT-2 came in, the number of parameters kept increasing. So if you look at it, like GPT-1 had 117 million, but GPT-2 expanded it to 1.5 billion parameters. Right? And then it started showing significant improvements in text generation, fine tuning, and creativity, right? And with GPT-3, the number of parameters went to 175 billion, right? And parameters are nothing but like different weights, and we'll look at like what all different weights really constitute. But GPT-3 is where they brought in a zero shot and a few shot learning, which is pretty much that a model can really understand what it has not seen before, and that's how our brains also work, right? We try to reason and figure out what object is by looking at its characteristics and details. And then when GPT-4 came in, this is pretty much like a great model. We have all been using it. It had more than a trillion parameters. It had all this, multi-model capabilities where you can put and give it an image, you can give it a text, and a sound, and it helps you, give contextual understanding and reasoning to generate what you are really expecting out of it, right? But having said all that, right, what really, when we have been talking about ChatGPT, using ChatGPT and all those things, but what does GPT really stand for? If we look at that, the first word, this is like built out of three words. The first one is generative. Um, when I say generative, it's pretty straightforward. It's a process. Uh, it's a. Hey, I think there's some noise. Yeah, thanks. So generative is like a straightforward word. It's the process of creating new data, text, or outputs. Right? Whenever we talk to, and that's where the whole generative AI also comes in, right? We are trying to generate new text out of things. Um, Pre-train is this second thing, which refers to a model which has been trained on a large data set. So pretty much the data set was like whatever we had on the internet, they just used that to train the models. And then pre-trained also refers to that it has more room for fine tuning. And we'll get to that, what fine tuning really means at the end. But GPT models are really trained on like vast amounts of data. And during this training, this model learns. And then we'll see like how it really, uses that learning to figure out what is the answer to what you're expecting. But at the end of the day, all these models were really more of a next word predictor. They get in a sentence and then try to predict what is the next word in there, but they also try to understand the context, right? Because that's where the game changed completely. Because even before LLMs, if we look at things like, let's say, Watson or Google's Dialogflow and things, they were also working on the intent entity model, but they did not have that much of context which they can use. We could not use a large prompt and things in there, and they did not have a way to fine tune up and do all this stuff, right? So pre-training, it generally involves having a large knowledge of vast amount of text, and it makes the model capable of handling various types of language tasks. But transformer is where it kind of changed things. So this is pretty much a deep learning model, and it's based on a self-attention mechanism. So we'll look at what a self-attention really means. But this has revolutionized the way natural language processing works, and this pretty much is responsible for the current boom that we see in the AI. Right now, this is actually responsible for maintaining the relationship between different words that we have, and then what are the different, regardless of their position, it leads to a context aware predictions actually, right? So having said that, let's look at this paper. So I don't know if you guys have gone through this, but this is where things started changing for the whole LLM space. This paper was it came up by Google, and this was primarily designed for translations of from one language over to the other. So when we do a translation, it does not really just involve a word by word translation, but you also have to understand the context behind what you are trying to translate. Now in that case, you need to understand, it's you have to look at the whole sentence and then see how the translation should happen, and that is where the transformers came in handy. Now, transformers could be of different types. Basically, just imagine the transformer is just a piece of a software. Now, you give it a text, you give it a text to a transformer, which is a text to a speech kind of a converter. The transformer will convert that into a speech and give a speech to you. And let's say you give a speech to a transformer, it can convert it out as a text, or you can do things like, you give a text to it and then it can converts an image for you. But how ChatGPT and the transformers, this whole really came in handy was it can take in a text, image, or speech. But the whole goal, as we said, it was to predict the next word of what comes in next. Right now, this sounds a little weird because if you are just predicting the next word, then how is it able to give you all the other, kind of things that it is doing? So if you remember, the initial marketing that was done for all of these LLMs and ChatGPT was that it can act as a storyteller for you. So when I say it as act as a storyteller, so you give it a sentence and then it can complete a story for you. And that's where the whole repeatability kind of comes in. So you give it one sentence, the next word is predicted, and we'll look at like how it really predicts that. But once it predicts that next word, it puts that back into the same software and say predict the next word for me. And that repeatable process keeps on going, which at the end gives you like a final full essay or a story which you can consume as a user, right? But till ChatGPT 2, the results were not very good, right? When GPT-3 is where we started noticing that something is really going on, and then people started noticing things over here. So let's look at what really happens under the hood when we say, a next word generator. What really goes on when you try to do that? Now, let's just take this word, right? Sentence. It says, life's too short to skip. Now, this is similar to the initial exercise we did, where the whole goal for this right now is to figure out what is the next word which really comes in, in this. Now, as a computer, as a human, we understand what life means, what too short and all of these things mean. But as a computer, it does not know anything, right? And we are more being on the technology side, we are used to this whole deterministic way of dealing with things, where we say, let's say we put a software and say 1 plus 1 is equal to 2, right? It will always give you the same result, but that's not how LLMs really work. Now, the first step which really comes in this whole under the hood is that we have to divide these things into smaller patches, because you cannot just put in a big sentence to a function and say just give me back what I want. It divides that into a smaller patches which we call as token. So there are different ways of tokenizing. Word2vec is one tokenizer, or there are different other ways of tokenizing, but let's just assume that we consider each word as a token. The LLM, the first step, what it does is whenever it sees a sentence which we have to generate something, the next word from it, it will divide these into smaller chunks and say, life is one token, two is one token, and so on. But still, the next step here will be that even the computer does not understand what these tokens even mean. So for that to happen, it has to convert them into vectors. So vectors are just like numbers with an n-dimensional space, but we convert them into vectors, and this is what the computer starts to understand now, right? Because the computer only understands numbers. So let's say if it's a n-dimensional space that we have, and then skip has one vector, short has one vector, and skip has one vector. So this vector will always remain the same, and this is where the whole learning comes in. When we say it has 175 billion parameters, or like a trillion of parameters, it has all its vocabulary. So whenever it sees the word life, it will always create a vector out of it, and it will always point into a particular direction. It will have a certain magnitude, and all the words which are similar to life or which are similar to short will always point in a particular direction, just to signify that these words are similar in nature. Now, and then these vectors really go over a series of operations with the aim to give a probability distribution of the next possible word. And this is where the whole, non-deterministic behavior really comes in. Because if you see that, let's say you get a probability distribution, something like this, where you say dessert is the vector food, and all of this have a certain probability of what might come in next when, you try to complete this sentence. But it is not telling you that this is what it is. This is the 100%. I'm 100% sure that this is what really comes in. And this is also, if you look at it from the way that we are trained as humans, we also see it in a different way. Because when we say life's too short to skip, it depends on the situation we are in, the way our training has happened, and based on that, we'll predict a word for it. And everyone in this room can predict a different word out of that, right? So what a LLM gives you is a probability distribution. And we'll also look at, there's another piece which really comes in, which is the temperature, and we'll see what role that really plays. But if you have ever worked with ChatGPT and you give it the same sentence every time, you'll see that it gives you a different result all the times, right? It's not the same results, and that's what brings in the creativity in it, right? If it keeps using the same piece over and over again, it kind of does not give that experience which it gives right now. um, but we are saying that we are using words as vectors. Now, what will happen if we really start using each character as a vector? Because we say that we want to chunk it down into smaller pieces and then use that pieces over and vector, and then maybe generate some relationship out of that. But if we start using characters as tokens, then L will be a separate vector. I, F, everything will be a separate vector in an n-dimensional space. But then getting semantic or getting meaning out of it will become very difficult. And also the amount of computation required to make this work will be like very huge. And that's whole the context here, right? We want to get a semantic meaning out of it, right? Because if we have a vocabulary where life is a word, then that would make more sense, instead of just saying that each of these characters are individual tokens and then each of these tokens keep talking to each other as a character. So now this is where we'll talk about this whole embedding metrics. So we said that we get a sentence, we converted that into smaller chunks called tokens, and then convert that into vector. Now, what that vector really means, right? Now, GPT-3 uses like an embedding layer, or any GPT model, they use an embedding layer to convert these tokens into a dense numerical vector, and these are all embedded in the weights itself. So each time you do it, it will actually give you the same vector for you. and they are initially random, picked up at random, and that's where the whole learning comes in. Because by default, these models are not learned. When you start, the vectors could point to some different direction, but as and when the learning happens during the pre-training phase, that's where you actually start assigning, weights to these vectors. Now, the size of the vectors really, the embedding matrix really depends on the vocabulary size and the dimensions of the embedding, where vocabulary size is just the number of unique tokens that the model has seen. For GPT-3, I think the number of tokens was somewhere around 50,000. And the embedding dimension is the dimensionality of the vector space. And we are kind of used to like a two or a. We, we are kind of used to like a 2 or 3 dimension, but these are huge dimensions that we have in the vector space, and that will also tell you the amount of computation required to make things work, right? And during the training, the model updates the embedding metrics to learn better representations of these tokens, right? So the initial embeddings are then fine tuned to create a more semantic and meaningful embedding for these vectors. But let's look at this. So let's say we say that each of these will have an embedding matrix, and this is the machine learning model that we have. And this thing is also a model, right? Now, if I ask you as an individual that what really a model means, you might give different answers for that, right? Because it could be a machine learning model, it could be a model of a project that you're building, or it could be like, a fashion model. But at the end of the day, we looked at that there's embedding matrix which converts a word or a token into a vector. This will always point to a particular direction, right? We saw that vector has like a magnitude and a direction. It's pointing to a particular direction in the space. But any guesses if this other model will have like a similar vector or a different vector? It will have a similar vector. So now what really happened? How would a software or a piece of software be saying that, what, we moved that, made it into a vector, and we said that it is being used, we'll just perform certain computations on top of that, and it should lead in the next results that we're expecting, right? But when we talk to a chat GPT model, we say this is a machine learning model or a fashion model, it can actually lead to, it understands it differently, right? And that is where the whole transformer architecture kind of really helped us. And this is where the attention block comes in. Now, let's look at one example here. Let's say I want to generate this image and I want to give it to ChatGPT and say, a white fat dog is sleeping on a beach. Now, what's the first step which would happen, right? I'll take this n-dimensional space and I'll put all these vectors using my embedding matrix, because each of these, let's imagine that we'll just convert these into white fat dog. Each of these will be individual tokens, and then we'll put them on the vector space. And if we try to use the embedding metrics, it says white is a certain vector that we have, fat, dog, and so on. And when we try to generate the image for it, and let's assume that we do not have any context going on in here, we might get this type of an image. Now, what's really wrong with this? Now, we said it's a white fat dog sleeping on a beach, but this is an image of a dog, and this is not wrong, but this is not what we expected, right? We expected probably something like this, which is a white fat dog sleeping on a beach. But even if we look at the way we humans really look at this, is that we say a sentence, we say, okay, there's a dog in there, and then are there any other pieces in the sentence which really, add value to this word, right? This word white probably adds in value because we're not talking of any dog, but we are talking of a white dog, right? And we're talking of a fat dog, and a dog is doing something. A dog is, at a certain particular place. Now, all of these, if we expect a LLM or something like a chat GPT to understand, there should be some mechanism for them to, talk to each other. And this is where the whole concept of self attention comes in, right? So, what self attention does is the way humans really process this thing. When we convert them into each token will have like a query key and a value matrix in there, right? Now, for each token, a query vector is derived, which says that what am I looking for, right? And that's how the brain was also processing it. We have a key metric, which says that what features do I have offer that others might compare themselves to, right? And then a value vector is derived, which provides some contextual information for which to draw. And now, one thing to note here is that we divided things into tokens, and each token will talk to each other token, right? And in the beginning, we said that the position of the words also do not matter. So, one is that the position of the word is embedded within the vectors, the embedding matrix. But we also have that these tokens are really talking to each other, right? Let's say we have a dog will talk to all of the other tokens. It doesn't matter whether you're fat before the word or after the word. It will actually talk to this to understand that is there anything, right? Is there any attention that this word needs to pay to the other, or this token needs to pay to the other token, right? When we say how much attention does the word fat pay to dog, because fat might not pay a lot of attention to something like a beach, right? And these scores are then calculated based on the query and the key metrics. And this also computes, counts as the number of, when we say 5 billion parameters, 1 million parameters and all those things, this query, key, and value matrices, they also combine. And that's where the whole overall weight for a LLM really comes in. But then we say we got something like attention score, which is computed by using the query and the key vector, and that's, imagine that's happening for each and every token. So bigger the size of the prompt that you have, more of these computation that you have to do. But one thing which is pretty interesting to see here is that all of this are parallelism, right? It does not matter. Normally when a human reads something, let's say if I'm reading the first sentence, I'll say the self attention mechanism calculus, so I read it from left to right. But when you give it to something like a software or a hardware which is like pretty capable of doing all this parallel computations, in that case I do not have to wait for some other response to get back before I start a new response. All of these can be done in parallel, which is where the whole revolutionization happened for this whole LLMs. Then we looked at the attention score, where we have this whole key and query vectors. We do a dot product of these and then try to find that. And then the attention weight. So then we get to a scaled dot product attention. So this is where the whole we scale the scores, so that we don't want to put emphasis on everything. We really want to put emphasis on really what matters, and that's where the whole softmax functions really do. We convert that into probabilities, so that we know that, okay, this is like a 20% probability of adding value to this, right? How much sleeping should contribute to beach, or how much, let's say, fat should be integrated into dog. And then we combine all of these, and that really gives you a vector. So let's say the initial vector was dog, but dog, when added with this weighted sum of value vectors, that actually gives you a contextualized representation of each token. And that's where we get to an image from a normal dog to this white fat dog sleeping on a beach, what we really wanted to create out of this, right? So this attention mechanism, it allows GPT to capture complex relationships between all the tokens, and then it improves the sentences coherence over there. So when we say that this whole transformer architecture changed the way neural networks really perform, attention was one of the major component which came in, right? So with attention, we were allowing the model to focus on different parts of the input at different times. So this whole self attention, it calculates the relationship of every word in the input, and then allows the model to weigh the importance of each word based on the context. And that's what is being learned throughout, right? And that all of these key, query, and the embedding matrices are being learned in the pre training phase as well. And the parallelism is like the biggest advantage of this, right? With all of the way the self attention really worked, transformers can process inputs in parallel. And that's the reason, if you have a bigger and bigger machine, you can do more work in there, right? Because if it is a sequential job, then you have to wait for one thing to complete, for then the next thing comes in. And this also leads to a faster training and a more efficient scaling. And what really worked with the whole LLMs and GPTs was that the bigger machine you put in, the more data you give it to it, it was actually providing a better performance every time. And it also improved the long range context, right? Because if you think about the older times when we were working with, let's say, the dialogue flows and something like Watson AI or Wit AI, the amount of sentences we could perform there were very less, right? That's because we could not parallelize things a lot, and then we were not really using a bigger machine and things as well, and the context was really missing, right? So this whole improved long range context really change the world from something like recurring neural networks or a convolutional neural networks. This LLMs really performed at a very big scale, right? And that's the concept of scaling also came in, where more data and more parameters, and that's why GPT-3 with 175 billion was good. But once GPT-4 came in with, let's say, a trillion parameters, obviously the amount of training it required, the amount of money spent in was really huge. But overall, it kept on giving better and better results in there. And this was like one other topic that we looked at when we said, it's trying to predict the next word in the sentence. And in that case, I mentioned a word called probability distribution, where we said that, it does not always give you the same results, but it gives you results based on a probability distribution. But what does a temperature really mean in GPT, right? So temperature is a hyperparameter. It controls the randomness of a token. Now, during the next text generation, it affects how the model is likely to explore different possibilities while sampling. So the temperature value could be higher, which makes the output more diverse and random. The tokens have more uniform probability distribution, and the results are like more creative, and you get unexpected responses. But if it's a low temperature, it produces more of a focused or a deterministic outputs. The tokens have higher confidence in, most likely choices, and it's more consistent and coherent response. Now, it really depends on the type of use case that you are catering to. If you want really, let's say if you are trying to, create a, you're a story writer or something, you would not expect your responses to be very deterministic in nature. You might expect your responses to be, more creative, so that if something even has a lesser probability, if you use that, that might come up with a better story. But if you are working in something, let's say, in a medical field or in some other field where you're, it's okay to not have very much a creative response, but you need to make sure that the responses are like accurate. Now, in that case, using a higher temperature makes sense, but otherwise, if you want, sorry, using a lower temperature makes sense. But if you want your, temperature, your responses to be more creative, you can use a different value of temperature and just play around with it. So now, we looked at these models and said that, these are like models which are capable of generating the next possible word for you. But then there's something called as fine tuning, and this is the reason why I touched upon the initial RAG based model, which we talked about in the last session, where, we have a model, let's say GPT-3 model, which is capable of generating the next text. We can fine tune that model as well, because this model is used for a very specific data set. It's not really it does not have your domain knowledge. If you want to do something like, let's say I want to do a pizza ordering thing, wherever the model is trained on, it's not really using that information. Now, what if I give you give the model all the conversations that are happening between a person who is taking the orders and the person who is trying to order a pizza? Now, in that case, if we'll have to update that model, or the model has to learn and the weights have to update in a way so that it can understand the the pizza terminologies, right? It can understand that the kind of data being used is really relevant to, the pizza ordering thing. But one thing which is really important in the field of AI is garbage in, garbage out, right? So you cannot expect it to get take like very bad data. If the data is not good on which it is being trained on, you cannot expect any good results in that matter, right? Whatever good software hardware you use, whatever good software you have for neural networks and this thing, you need to make sure that, the data which is being used to train a model, this is good, right? And then there's a distinction between like this whole fine tuning process and then training from scratch. If you have training from scratch, then, you have this all these weights which are assigned to a model, and they are just assigned at random in the beginning. But in case of fine tuning, you're fine tuning on an existing model, and that's the reason fine tuning takes in less cost as compared to, training from the scratch. And that's the reason why it's really getting easier for people to start fine tuning, let's say something on top of GPT-3 or any other open weights model, and then just use your domain knowledge and use different types of, fine tuning techniques to get something out of that model. Now, there are different types of fine tuning techniques that we have, right? Let's say a self supervised learning, where the base model is pre-trained using self supervised learning, right? This involves generating labels directly from the data itself. So it does not have something like an input output kind of a format, but there's no manual labeling required, right? It makes scalable across vast data set. You can just dump in data in there from a particular domain, obviously, and then it will just learn on the fly for you. Now, supervised learning is where you can train it for a specific task. Let's say something like a sentiment analysis, where you have inputs and outputs labeled, where you say, okay, this is a positive sentiment, this is a negative sentiment, and that's where the whole you can even provide an input output saying this is for this particular type of a question. This is the answer that you expect from the model to get, and then based on that, it can actually learn itself. And the third type of learning which really comes in is more with the reinforcement learning with human feedback. That's RLHF. And a lot of these tools that we use, or a lot of the AI tools existing that we use, there's a term called human in the loop, where we try to get the feedback from humans. Because let's say if we are learning something and then a model is giving out some input output from there, it might not work with a human preference, right? It might align with what is there on the internet and things, but maybe as a domain expert, you know it better, and then you feel that okay, this is not how the model should behave, but model should behave in a different way altogether. And that's where you bring in a human feedback and have a feedback loop associated with it, which helps you train the model better, right? And it makes the model more safer, more aligned, and capable of generating responses that adheres to human expectations, actually. So this is another type of fine tuning technique which has come up recently. So basically, what happens in a full fine tuning that involves optimization, or training all the layers of the neural network, right? Let's say if you have a big model with a large number of weights, it is a time consuming or a resource consuming process, right? Even fine tuning on a bigger model will obviously take more resources for you, right? But LoRa is like another type of fine tuning technique which is specifically designed to reduce your computational cost and memory, right? It kind of introduces an efficient method so that you don't have to modify all the weights. The original weights of the models are frozen, but it adds in like extra weights which are modified, which kind of reduces your scope of fine tuning. So now, instead of updating all the parameters of this large model, now it just trains certain low rank matrices, right? So these are like very small matrices as compared to the model, and then these are very task specific things, and then only these low rank matrices are trained, right? We don't train the original model weights. They are kept frozen, and that reduces the amount that you spend to train the model, right? And we are only focusing on these additional matrices, actually, and then even the same base model can be reused across multiple tasks, which are requiring like multiple fine-tuned copies of it. Maybe you want to train once for a medical space, or other training you want to do for some other space, so that can be done. And at some places, this LoRa technique has been better than a full fine tuning model, right? Because a lot of times what happens is that you start with a pre-trained model, you try to fine tune it, but all of your existing weights also get disturbed, right? Now, if you really fine tune it in a wrong way, then even the existing weights kind of go for a toss, and then it can actually give you worse results than it was actually giving you earlier. And again, this is pretty much a simple thing where for all the weights you add, let's say, a delta w as well, and these are all matrices. And then a and b are pretty much the low rank matrices that you associate. So all of the weights do get updated for the model, but it's just that you're not training it on those particular pieces itself. And then again, the benefits of LoRa are pretty significant, because given that the number of parameters used are less, it reduces the GPU memory usage, and then multiple tasks can be done by the same model itself. And also you can actually fine tune on a very large model, because you're not getting everything into your memory. So it does not matter whether the base model is large or not, but given that you're only working with this niche extra weights that you're adding in, so it kind of makes your fine tuning process easier. Now, if you look at the challenges of LLM, right? We talked about, let's say, fine tuning or other pieces around it, but still there are a lot of challenges which are there in the way the LLMs work, right? One is that safety and bias continues to be a big problem, right? Because all of these data, when we say a model has been trained on a certain data set, this data set is coming from the internet, and let's say a large majority of that data is based on human opinions, and then the models get trained on these opinions and things, and it's not we are not sure that whether that's the right thing for a model to be trained on or not. Hallucination is one other aspect which is there. They are very confident in saying the things which they are, which is wrong, but it says it in a way that it feels that okay, that's the correct thing, right? Because the universe that we have is huge in case, and that's where the concept of rags or really fine tuning it for a particular task really comes in handy. Because when you say hallucination, if you're using it for some mission critical process, it becomes slightly difficult to rely on these LLMs. That's the challenge that we also saw in some of the assignments that we did with our customers, where we added, let's say, LLM in there, but if we get in a long response from that, and we get it at and they say that okay, it's the right response and things, it becomes slightly difficult for us to really manage at that point of time. The cost is like also one big factor, right? Even not just the pre-training of the model, even the fine-tuning, obviously things like LoRa and QLoRa are coming in, but the cost aspect is always huge, because these are hardware intensive processes, right? As and when the number of tokens or the number of parameters keep on increasing, we add in more parallelism, the dimensionality of the matrices keep increasing. Now in that case, the cost will obviously keep on increasing, right? So even for fine tuning something, you can end up spending millions of dollars if your data size is huge. If the data size is less, you'll end up spending less money, but at the end of the day, you'll not get the results that you're expecting, and it won't be as comparable to all the other things that we have. And ethics also, this has been a big challenge. There are a lot of governments which are actually coming together and trying to solve this problem, but this will always be there. That there was one music company which came in called Suno, and they were using they could be using copyrighted music materials to train their models, right? You need data to train your model, you need the learning from there, but if that learning is coming from copyrighted materials, that will always remain a challenge for us. And then obviously it will be used on harmful acts. There have been a lot of cases where someone can mimic you, they can make calls, and they can use your voice to do stuff. So these are the things that we have to be they will come in, right? All the scams and things will come in. It's just that if we use AI for the right purpose, I think that's where it's going to be good. But having wrong expectations from AI is also bad, right? We should not just expect AI to just throw in some data in there and expect that this LLM will just do wonders for us, right? It cannot solve complex problems. It cannot just do whatever you ask it to do. You have to make sure that whatever data you are throwing into a LLM, it actually is also, you can, as a human, you can get that answers out of that data, right? Otherwise the LLM can do something which is, it can do it at a scale, but it cannot do, let's say your data is not able to answer, or it's not capable enough of answering something. You cannot expect the LLM to just magically do something, and then you'll get into all these hallucinations, or it will not really give you the right piece of information actually. Now, this is pretty much my last slide, and then we looked at the whole. In the last session, we looked at RAG and then fine tuning. Now, what as a next step, what we are doing is we're trying to compare how RAG and fine tuning really works, right? When should we use what, right? Is RAG not good enough? Like, why do we even get into something like fine tuning? But there are a lot of factors which kind of comes in, right? Let's say if your knowledge base is updating dynamically, right? You are accessing some external source system, and then you're getting the data in from there. Now, in that case, if your data keeps changing every now and then, using something like fine tuning will not be very efficient, right? Because your data keeps changing, and then just converting the data into vectors and then using that plugged into a LLM makes more sense. And if cost is like one factor, because fine tuning has initial cost involved, so if that is like a factor out of view, then it does not make sense to go with something like fine tuning. um, you know But with fine tuning, you can actually save the cost. If the number of calls that you're making, and then every time you are using your prompts, your tokens, now in that case, something like fine tuning will kind of really come in handy, and you can just uh, you know maybe say once in a month or once in 2 months you'll train that model, and at the end of the day you'll get a better domain knowledge in there, and then you'll keep on increasing on top of that, because the beauty of fine tuning is that once you can fine tune, and then on top of that you can keep on adding in more data. But it's just that if your data keeps changing drastically on a daily basis or something, or if you're expecting to call some external APIs or something, I think that's where things really come in handy. But this whole all of these considerations of cost and scalability and things really come into the picture when we really decide. So what we are doing as an exercise is that we are trying to just do use RAG and fine tuning at Tarka Labs for the same set of data, and we'll probably just post the numbers that we get on the social channel, just to see like how things really behave and what's like the best thing to approach in a certain way. And yeah, I think that's all I had for this session. Thank
Thank
you.
you so much, Harman. We will take some questions. If there's anybody, please unmute yourself and can take in some questions.
So hi Arman, at this side. Uh, so from your point of view, what would be the limitations for the LLMs?
Can you be a little specific in your question?
Like by uses uh, I mean to say is there any limit we can use? There is no specific things we can do. We can do everything right in LLM by using ChatGPT and all the AI. But is there
Mhm.
any harmful for us? Like is there any
So
disadvantage?
when you talk about limitations, so one thing which I had in mind was at one point we were actually trying to solve something like a traveling salesman problem, if you have heard of that. So we were expecting that we'll just give a big Excel sheet to the LLM and say, just tell us how should I plan my warehouse management and all of these things, right? So those kind of things for that LLMs are still not there, right? That's not what it is meant for, and we should really use it for things which it is really meant for in that case, if that answers your question.
Yeah, yeah. Thank you. Satisfied.
Is there anybody else who would have any questions? We can take one or two more.
Hi, Harman. Riya here. Just wanted to ask, initially you mentioned that the tokens that we have in LLMs are basically vectors represented. And so basically, if I have a word like life and something called as lively, then they kind of need to point in the same direction because there's some context that is matching between them. But you also mentioned that initially when LLMs learn these vectors, it's through some random matrix. So how does it, I mean, how do the vectors change over time as
No, it's not that it change over time. It's more of that when you do the pre-training, you learn from the data that you get, right? So when you do a pre-training, let's say you give it some data and say this is the right thing, right? Because when you learn on something, let's say if I tell you A, B, C is something, then you'll know that it is it. So during the concept of pre-training, that's where your weights, the LLMs learn, and that's where your weights of these things change, right? So let's say you start with a certain vector pointing in a certain direction and a magnitude, and then it learns over the course of training this thing that this is how it should point to, this is where the direction it should point to, and this is where all the similar vectors also should point to, so that it can actually get some semantic meaning out of that. So this change of the vectors they really happen during the pre-training phase. And then whatever models we see, if we use something for fine tuning, and that's the difference I mentioned, right? When you train a model from scratch, you assign them random weights or you assign them random matrices. But once you try to fine tune a model, there you start from this pre-trained values, right? So all this embedding matrices and all this query key and value matrices, they'll have a certain value which is their part of that pre-training model, and then you fine tune on top of that.
just to understand correctly, these vectors are essentially represented as matrices, and like uh, when it goes into the training phase, we are essentially adding something to these metric vectors or rotating them or scaling them.
That is correct. We are kind of updating these matrices to give us the right values. Not the right values, but what we really expect the LLMs to do.
Is there anybody else who would have anything?
Yeah, I just wanted to ask a question that how do you fine tune the LLMs without overfitting?
When you say overfitting, like not just, what does that mean?
Like overfitting as in when the like as we understand that when you overfit the model, there's a huge amount of data set involved, and it actually goes through the exact points instead of generalizing the thing as a whole. So when there's an
So
overfitting involved,
that's
I
more
find
of like,
it
you'll have to
confident.
test it out. So as and when you keep on fine tuning, it's not just a one time process. You cannot just say that you just fit in there, you throw the data and then it just works for you. That's where this whole retraining process comes in, right? And then you have to really see what really works for your use case. And then obviously, right, if you keep fine tuning and get to a state where I talked about this whole catastrophic fine tuning process, where you change the original weights itself so that your fine tuning, instead of doing better, it started getting worse, right? So it's more of like, I think the retraining is where kind of really helps, or then a feedback loop, I would say.
Thank you.
Just a last call. Is there anybody else who would like to have a question? Otherwise, we'll end the session.
Harman, how is the retraining done for coding? For example, you have GitHub Copilot, right? Like, how is this retraining?
Hey, sorry, this is not.
Sanjeev, I believe your voice has a lot of background noise. Could you type in the question maybe in the chat box?
Are you able to hear me now?
Yeah, it's kind of.
Okay. Are you able to hear me now?
Yes.
Okay. So I wanted to know this. The natural language is understandable. Like, how do you think the training would have been done for GitHub Copilot with just the coding? Actually, right?
You mean for
And that
code,
too,
right?
yeah. How is it
Okay.
being done?
When you say natural language is understandable, it's just because we understand it. Like, because imagine
Yeah,
for a computer, it does not matter, right? Whether it's English language or whatever. It really depends on what you're using to train a model, right? For a computer, it's more of, let's say you say that this parentheses are a token in that matter, right? And that's the reason I said then in normal English, it's fair to say that you convert your words into tokens. In case of a coding, your token will be different, right? Because in that case, let's say in normal English, your brackets, parentheses might not make a lot of difference, right? And that's where your vocabulary keeps on changing. The data which it is trained on is not like a normal English data or any other data, but that would be like some actual code which is there, and that's where it learns from.
okay. And Herman, one more thing, right? We keep hearing about this parameters and tokens. Like any of
Hey,
these
sorry,
models.
it's getting very difficult.
Sanjeev, could you please type the questions maybe in the chat box? There's a lot of
Are
background
you able
noise.
to? Gosh. Is it better now? Is it the same thing?
No, Sanjeev, it's still a lot of background noise.
Okay, no problem. Let's leave it. Let's do it. Take it on.
Yeah, sure.
If there's nobody else, we'll end the session here.
Right.
Okay. Thank you all. We will send you guys a feedback form. If there's any questions that you would like to ask, we'll be happy to answer them. Please take a look at the feedback form after the call. And if you want to look at the recording, it should be available on Setting Technologies YouTube channel. You can always go back and take a look. Thank you so much, Harman. It was a wonderful session.
Thanks a lot, everyone. Thank you. Bye-bye.
Thank you. Bye.